As I usually tell people, if you have any questions along the way, please do feel free to interrupt me along the way. I'm good with it. 3 kids, I'm used to it. As usual, also, we will send you out a copy of the slides after this is over and a link to the presentation on YouTube. So with that, I'll kind of give you an overview of where we're going to go through. I usually start these off with a couple of slides about who Inside Analytical is. So I'll go through that fairly quickly at the beginning. And thanks, Cindy. I'm so glad that somebody appreciates. I try to have a sense of humor. We're going to talk about who Inside Analytical is, and then we'll talk a little bit about carbon capture and kind of some of the principles behind it. I think this should be principle ELES, not ALS, but that's okay. And then some of the contaminants that we worry about when we're doing carbon capture, and then how we might go about doing compositional analysis. So Inside Analytical, we're a Calgary-based systems integrator, manufacturer, distributor. We operate out of Northeast Calgary, a fairly large facility up in the Northeast. Large manufacturing floor available to us. Good access. We'll do everything from full analyzer buildings in there to analyzer sample systems. For the Canadians who are aware of the requirements for CRN, we're an AB 83 compliant fabricator. So everything we build, if required, will have a CRN number on it. And a lot of the folks that are here, for those of you that don't know me, kind of my undergrad background was physics, grad work chemistry. Spent a long time working with Western Research and Amitech along the way, both as a contractor and as an employee. A lot of the folks that are here are people that worked with me while I was over at Amitech. So although Insight has only been around for, say, 6 or 7 years, lots of us have a lot of experience. So I got a great documentation team, drafting team, some really good design resources. We 3D model everything we're going to build, do a great job on our drawings and docs. Journeyman instrumentation guys, journeyman electricians, do full factory tests, acceptance tests here in Calgary. We pride ourselves on having full systems integration capabilities. So we'll do everything from custom analyzer sample systems to process analyzer integration, PLC and automation works at full analyzer buildings. We like to work with our customers, ideally from as early on in the project as we can, right from that front-end engineering design through detailed engineering, through to fabrication. We'll do on-site commissioning work. And what really makes a difference in the analyzer business is we have to ensure that we provide great service. And so we like to provide service for all the products that we sell, factory train all of our techs. I used to teach courses internationally about analyzer sample systems. It's one of the things I believe that we do really well, or we make every effort to at least, and we're certainly aware of the issues that can come up and try to make sure that we don't design any of those issues in. So we'll talk a bit about carbon capture. There's an article that just came out in Bloomberg recently talking about how carbon capture is going to be growing. And so this slide just shows carbon capture capacity by source. And they break it out from natural gas processing through to ammonia production. Because, when we talk about ammonia and steam generation here, we tend to be talking about steam methane reforming. And so one of the big things right now is for all these guys who are running SMRs is saying, well, how am I going to lower my greenhouse gas footprint? And they're going to do that by doing carbon capture. One of the ideal facilities for doing that power gen is, of course, a reasonable existing one and one where we see it growing as well, and the natural gas processing side. In Alberta here, this oil refining piece is quite important as well. When we talk about steam-assisted gravity drainage and producing from the oil sands in the methodologies that we do, which generally involves a lot of energy consumption, COSIA and that whole oil sands alliance group has been looking at putting CO2 capture and big CO2 pipeline structure in. So we will talk a little bit about that CO2 pipeline structure that's anticipated for Alberta as well. So what is carbon capture? What is CCUS? We hear this term CCUS. It's carbon capture, utilization, and storage. So there's a bunch of pieces to it. Usually there is some kind of obviously carbon capture part to it. We got to get this CO2 from someplace. It might be from power generation. It might be from chemical processing. So from industrial processes. And I've put these in different colors because industrial processes, especially ones that run at higher pressures, it is easier to do carbon capture if the CO2 is at high concentration and at higher pressures already. Because we're going to talk a bit on the next slide about how we actually do the capture. And it works better at high pressures and high concentrations. So it's easier from from industrial processes that have some pressure to them. Stack gas emissions often at least have high CO2, even though the pressure is lower. And then you'll hear people talk about direct air capture, capturing CO2 out of the ambient air. And that's a lot more difficult because the concentrations are lower. On the utilization side, we see a lot of it get used for enhanced oil recovery. We'll see greenhouse gases in food applications, and then manufacturing with things like cement applications. We'll talk about each of those quite briefly. And then from the storage side, it is almost always being stored to some kind of underground reservoir, whether it's an old oil well, an old gas well, or new wells being drilled into some saline aquifers. So on the carbon capture side, I thought this graphic was kind of useful to put up. There are a number of different technologies that are available for doing carbon capture. And so on this x-axis down here, we're talking about the technology readiness level, or how well commercialized is this technology. And you can see that liquid solvents really stand out there. And liquid solvents are useful, especially because they can also handle very large volume applications. So when we start talking about, say, an oil sands producer who may be producing a lot of carbon dioxide, these liquid recovery processes are going to be the ones that are most likely to be used to capture that CO2. These are, as we said, the most advanced technologies. They're also a very well-established technology in gas treating. Again, Alberta is kind of a very suitable place to be doing this because we've had a long history of treating acid gases, CO2 and H2S. A lot of the gas fields here in Alberta have a lot of carbon dioxide in them and have a lot of H2S in them. And so we've been doing amine treating carbon capture for a long time. It's just a question of what more H2S capture, but then you'll also see people doing acid gas reinjection. It's also suitable for the very large volumes we're going to end up dealing with here. And the common amines is mostly MEA, monoethanol amine. MEA can be somewhat corrosive, and so people will use other amines like diethanol amine and diethanol amine. But MEA is very cost effective, works really well, and so you'll see a large part of these will be MEA based. If you're interested in aiming for carbon capture, there is a company called Sulfur Experts. They have a division called Amine Experts, and they are the guys to really talk to if you're looking at, hey, I really would like some more information about how I can use amines to do this. Then there's the carbon utilization piece. What are we going to do with this carbon if we're going to try to use it for something? So we talked briefly about capture. Let's talk a little bit about utilization. Certainly the largest and most advanced right now is to use it for enhanced oil recovery. So right now, so I think my screen got me. There's a company called Enhance Oil, and they take a bunch of CO2 that's been captured through the Alberta Carbon Trunk Line and use it to re-inject into wells. The CO2 acts as a solvent, if you like, to help pull some of the oil out of the wells, produce it again, and it can improve oil recovery. So this is a great application here in Alberta. If we look at it though, there's another one where another application which has a great degree of technology readiness. Technology readiness level 9 is pretty much the highest. It means it's fully commercialized. And so the other thing that can readily be done with the CO2 we capture is we can introduce it into concrete. And that has a number of advantages associated with it. Two primarily. One is it captures the CO2. So basically, it takes that carbon dioxide and it now gets introduced into the cement, but it actually also increases the strength of the cement. So we actually don't have to use as much cement to build a structure with the same level of strength to it. And so it means we use less cement. Cement is in itself, cement manufacturing is a very CO2 intensive business. And so being able to use less cement and make stronger cement and capturing some CO2 into it is great. And there's a big project going on in Edmonton. Company, I'm going to spell this wrong. Heidelberg is got $1 billion investment going on up in the Edmonton area. They'll build what I believe is going to be one of the world's first zero emission cement facilities. There's a number of people also looking at making activated charcoal or activated carbon out of it, making carbon nanotubes. These technologies aren't quite as advanced, but there's a number of places that we're seeing the CO2 potentially get sequestered. There's also the greenhouse gas applications, the beverage applications, etc. Or not get sequestered, get utilized. This photo down here is actually a photo of the Heidelberg facilities. And then there's the storage piece. The Western Canadian Sedimentary Basin has some really, really well-suited formations for this. So again, Alberta, Saskatchewan, we're in a really good spot to be able to do carbon capture. Primarily into these saline aquifers. The idea is we can take this CO2, inject it down into an aquifer. Typically, these are over 1,000 meters deep. And so these are fairly deep reservoirs. The big thing is they have to have a good cap structure for them so no bubbles can come out, escape back up to the surface. We ideally would like them to be large. Alberta has the ability to capture over 1 billion tons of CO2 into the saline aquifers that it has. So we want large capacity. We need it to be in a porous structure. We're going to want to inject gas in it. So we need good injectivity. So again, we've been starting to characterize a lot of these reservoirs for decades now, or a decade now. And determining whether we have a good reservoir that's able to be used for CO2 injection. And then again, like I said, good cap structure is important from the containment side. And so what was interesting is at the Carbon Capture Conference up in Edmonton, and one of the speakers there was comparing carbon capture in Canada to land-based carbon capture in the US. And one of the big differences is in Canada, when you buy land, you don't get mineral rights, typically. And so you have surface rights. This is different in the US. In a place like Texas and Oklahoma, typically you get the mineral rights with the land as well. And because these reservoirs can cover a large area, if they're going to do CO2 injection, they have to negotiate the mineral rights with each of the individual landowners. Because in Canada we don't sell mineral rights with the land, it's conceivably going to make it easier to develop a lot of these CO2 reservoirs. The US, there's a large movement to doing the CO2 sequestration offshore because nobody has mineral rights offshore. When we're going to think about doing that, though, if we're going to do this carbon capture, generally the facilities we're going to capture it at are not going to be nearby where we're going to do the sequestration at. And so one of the things that we have to consider is the transportation of that CO2. And so what will typically be done is this will be transported into a pipeline someplace for storage. So the map on the side here kind of shows what's going on with the Heartland Industrial Complex and some of the Alberta carbon trunk storage that's going on in there. But, we've got this Heartland Industrial Complex up by Edmonton. We're going to have carbon capture going up there. There's a lot of refining and petrochemical up there. Pipeline that down where it's being used for enhanced oil recovery down in the Lacombe area. And this is where Enhanced Oil is running a lot of their CO2 injection for oil recovery. These are typically very high pressure pipelines. They want to put as much CO2 into there as they can. And so they compress it. They typically want to get above the what's referred to as the supercritical state or get into the dense phase. And the critical pressure for CO2, for pure CO2, is about 1,070 psi. So they have to be above the critical pressure, which is, so again, these are pretty high pressure lines. And we'll see them running as high as up to 2,000 pounds. The Alberta Carbon Trunk line that's being built and operated by Wolf Midstream, pretty big line, 16-inch line. When we're getting all of this CO2 from industrial sources, whether it's from power gen, whether it's from oil sands production, whether it's from an operating refinery, we have to be concerned about the CO2 purity. And really, we want to be concerned about it for two reasons. One is we'd like to know what our CO2 percentage is. We, in Canada at least, have a carbon tax. And so companies will get credit for how much CO2 they capture. And so it becomes a big deal because in these large pipelines, at these high pressures, we have very high volumes, volumetric flows. And so the difference between 95% or 96% CO2 is 1% of the total flow. And it's 1% of your total carbon credit. And so being able to measure the CO2 purity in that, close to 100% CO2 range, be nice to be able to tell the difference between 99, 99 and a quarter, 99.5% CO2. So we want to know the CO2 purity, but we also want to know what contaminants are in there. Especially since we're dealing with supercritical CO2, it's a really good solvent. So it can pull a lot of contaminants in with it. The contaminants we're often interested in are things like nitrogen, oxygen, argon, components from air, especially if we're doing it from stack gas. If we're doing it from stack gas, things like SO2 will be important. NOx can be important. And then depending on the chemical processes it's coming from, H2S, carbon monoxide, hydrogen, methane. This one especially is important. Water content, because it can be a contributor to corrosion, can be a contributor to hydrate formation, and also water is very soluble in supercritical CO2. So what will happen is if our CO2 is supercritical, it can dissolve a lot of water in it. And when you lower the pressure, water will actually condense out of it. So there's a bunch of reasons why we'd like to know these things. They affect the phase behavior. They can affect corrosion and safety issues. They can affect upstream equipment. So if we're doing injection wells, we want to be concerned about, am I putting in something that's going to damage perhaps my pumps, especially if I'm going to hit water dew point issues, things like that. They can provide us feedback on the process operations. So they can tell us how well our CO2 recovery plant upstream is actually working if we're measuring these contaminants. And then there's other contaminants that aren't shown here that are of interest, but we can be worried about things like glycol that's coming from the dehydration processes, like methanol that might have been added for freeze protection, or amines that have been used for the carbon capture side of things. So we are, well, I'm going to talk about that more when I talk about the mass spec. So on that CO2 sequestration side, it is potentially quite big. Again, here in Alberta, if we look at the Pathways Alliance group, which is basically all of the major oil sands companies have come together to say, we should put CO2 capture in, we should build CO2 pipelines. And so the figure that's shown here is from one of their documents, which talks about all of the nodes and the points that are going to happen within this CO2 pipeline. And so if you look at this, you can see, well, it's kind of hard to read, but we have Curl and Firebag, a bunch of the Suncor facilities, Imperial Oil facilities, all feeding into that first phase one pipeline. We have Cold Lake, we have Cold Lake, Imperial again, Christina Lake, Meg, Christina Lake, Synovus. And so all of these guys are planning to feed into a major pipeline infrastructure that will then bring a lot of that CO2 down into that Fort Saskatchewan area. And so because we've got a lot of components that we would like to be able to measure, if you look back at that previous slide, and we talked about a lot of different chemicals we would like to be able to do an analysis for. And so in an ideal world, we would prefer not to have to put an individual analyzer in for every component. And so because of that, mass spectrometers become one of the ideal solutions for this. Mass spectrometers are, if you like, a universal analyzer. They can measure pretty much every individual, every component. They get a response to every component. They can separate them out. So we can do a full analysis of all the individual components. We can do that in near real time. We can do it down to low ppm, even to ppb levels. At the same time, we can be measuring CO2 purities up at the 95 to 99.9 percent purity sort of range. So we can get how pure is our CO2 for that CO2 tax credit side, and also be doing an analysis of all the individual contaminants. So Insight has the pleasure of working with Extrel. Extrel is now it's a Process Insights company. Process Insights is a holding company that has a number of different analytical technologies within it, and the Extrel mass spec is one of them. Extrel has been in the industry for a long, long time. They talk about here a 55-year history, and I'm not sure how old this slide is. What I do know, one of the things that was always, I always tell this story when I talk about their equipment, but what I do know is that when I did my grad work, when I was doing my grad work back in 1983, I did it on an extra nuclear mass spectrometer, and extra nuclear became extra. So a long history in the mass spec industry, fast, accurate analyzers that give us lots of information. Because we can analyze multiple components, we can use this as a means to get information about what's going on in the process. We've got a large service and support network and the largest installed base of process mass spectrometers. So when we talk about a mass spectrometer, what are we talking about? How does it work? There's a vacuum pump. Shown down there is a turbo pump. And this whole chamber is kept under a very high vacuum. That vacuum sucks a sample of the gas in. It goes past these two filaments, which make up what is called the ionizer region. So a molecule that comes in, let's say it's a CO2 molecule, it ends up getting a positive charge on it. The filaments are boiling off electrons that are used to ionize the gas. There's also an assembly in here that we often refer to as the ion lenses. And they are negatively charged, so they attract that positively charged ion towards it, and they guide it through this little hole that gets it into the quadrupole mass filter. Quadrupole mass filter has a high frequency AC varying voltage being applied to it. This current going through the quads, it basically provides a variable electromagnetic field that, depending on the frequency, determines what mass ion can make its way through the rods and get over here to hit a detector. And so, depending on the frequency we are operating the quadrupole at, only one mass of ion can make its way through the quadrupole mass filter. And what we do then is vary the frequency on the quadrupole mass filter and basically scan across all the ions that we're interested in. So when we ionize something like methane, we can get a CH4 plus. It'll have a mass at 16. Carbon's 12, hydrogens are 1 each. So CH4 has a mass of 16. But we can also have that break up and give us a CH3 plus peak, and that's going to have a mass at 15. So we get, similarly, we can get a peak at mass 14, 13, and 12. We use this fractionation pattern to help identify what chemicals are present. So the molecules that come in, they get hit by that beam of electrons, they get ionized, they fragment. We measure the ion currents at different mass fragments. Because we know the mass that it was at, we can use that and calibrate that for a given molecule or chemical structure. Mass specs have a bunch of advantages in that one is that they have very fast analysis. So they can do a full analysis of the gas stream in seconds. They can pick up pretty much any gas or vapor. As long as we can get the molecules up in the gas phase, a mass spec can detect it. So which means we don't need to have as many analyzers. We can separate each of those species as well. So depending on the applications, we may want to look at different hydrocarbons, different sulfur compounds, different solvents if we're doing a solvent drawing application. So we can do this, again, this multi-component analysis with as few analyzers as possible. Just because we can measure any gas doesn't mean we can measure any gas, though, in any mixture. So sometimes we may go, although we could do that on a mass spec, in this mixture we can't, and we'll add another analyzer in. So we'll talk a bit about that as well when we get into these CO2 pipeline applications. Mass specs are capable of doing detection limits down in the parts per trillion if we use atmospheric pressure ionization. More realistically, we can typically go from ppm to percent levels. And they are very linear in terms of their response factors. And so a single point calibration can often be used, again, from that ppm level all the way up to the percent levels. The external mass spec, at least with the RTG2, comes with its own air or HVAC system. Mass specs, especially if you want to do low-level detection limits, it's good to keep them at constant temperature. So there's a built-in HVAC on the unit. It's got a user interface based on basically a Windows touchscreen computer. Often a 16-port or more inlet manifold valve. So we can analyze up to 6 streams. These might be calibration streams or sample points. So multi-point capable. And again, when you have a really fast analyzer, 0.4 seconds per component, it means if I'm doing 10 components, it only takes me 4 seconds to do that analysis. So now I can switch between multiple streams. From trace ppm up to 100%, linear response, speciated. No consumables, no carrier gases are needed. Available for hazardous areas. And in carbon capture applications, we can do things like the CO2 purity. Some of the common contaminant gases they like to look for, things like methane, sulfur dioxide, H2S, argon. Our client right now that we're working on a project with wants to do methanol, ethanol, and glycols in there as well. I remember actually you want to do glycols or amines, but it's interesting. So in the application we're doing with a mass spec right now, we are basically doing the CO2 at 99+%. So one of the things we wanted to demonstrate to our client was we can measure this at 99.25% and tell the difference between that and 99.5%. Because again, this comes back to the dollar figure value of that tax credit. But we're also measuring methanol and ethanol, I think at 16 and 23 ppm respectively. I'm trying to remember, it was the glycols or the amines that we're doing down around the 3 ppm level. So we can measure from pure components right down to ppm levels of different contaminants. So again, like I say, you'll get a copy of all these slides. If we look at what we're able to measure with the Process Insights devices, I was going to mention, I guess, on these contaminant side things. You'll notice here that H2O is not listed as one of the contaminants that we do on the mass spec. So we will often put a separate analyzer in to do the moisture measurements. And so in our case, we are using a Tiger Optics cavity ring down spectrometer, can do trace moisture. So you can see, we're showing over here measuring in the ppb levels. Typically in these sorts of applications, we'll be measuring in the 50 ppm kind of range though. You'll also notice that CO is not listed here. And so we can use, in some cases, a Tiger Optics or another technology to measure the CO. And why not on the mass spec? In other applications, we would use the mass spec to do the CO. However, we said when we ionize a molecule, we can measure the CO it can break into fragments. And one of the fragments we get when we ionize CO2 is we get a CO fragment from it. So what that means is CO2 is at mass 44. CO is at mass 28. Sorry, 30. No, 28. And so what that means is as my CO2 goes up, my peak at mass 28 gets bigger and bigger. If I wanted to measure the CO in the process gas, it has a peak at mass 28. So now I have difficulties telling, is my peak at mass 28 getting bigger because my CO is going up or because my CO2 is going up? And if I want to measure trace amounts of CO in the process gas, it may not be suitable to do it on the mass spec. If my CO2 is very pure and has very little hydrocarbons in it, I can do that measurement on the Tiger Optics device, or I may use a third party, another manufacturer's non-dispersive infrared type analyzer to measure the CO and the CO2. So right now, Insight is doing a full analyzer shelter for a carbon pipeline application. We're using the extra LMS to do most of the components. We're using a Tiger Optics to do the trace moisture. We're doing a third-party CO and CO2 analyzer based on non-dispersive infrared technology. Custom sample system for all of those analyzers and building that into a complete turnkey solution. So when we start looking at these CO2 pipeline applications, we're going to want to look at what is the source of the CO2, because that's going to determine to a large extent which components we want to measure. We'll only usually see SO2 if it's coming from a stack application. Some people will say they want to measure SOX or SO2 and SO3. So certainly a mass spec can do the SO2 and the SO3, but there's really not likely to be any SO3 in the stream. So again, we want to have some understanding of the process. When we're doing CO2 capture, we often have to strip the water out of the system. And SO3 in water goes to sulfuric acid, so SO3 goes to the aqueous side right away. So it's very unlikely we're actually going to see any SO3 there. Similarly, we will see NOx in there only if the source of the CO2 is likely coming from a stack or a combustion type application. H2S has most often been stripped before it got into the recovery process, but we do see this showing up in some petrochemical applications. Inert gases, people's hands want to know the inerts there. So the nitrogen, the oxygen, etc. This one is going to be prevalent in all of them. This is probably, arguably, one of the most important measurements that we're going to do. So we're going to want to look at providing a reliable, accurate moisture analyzer for these applications. So, and again, things like glycols and alcohols, etc., are going to be determined a lot by what chemical processing is going on upstream. So realistically, we need to put together a really good application review of what do we need to measure and why. Oftentimes, if you're an engineering company or if you're an analyzer vendor and people are coming to you with the application, they'll often give you the entire shopping list of, I want to measure all this stuff. But when they start to see that that adds a lot of complexity, they'll tend to refine what measurements they're really going to need. I was going to add some stuff in here. I didn't realize how quickly I was going to get through this. I was going to add some stuff in here, so maybe I'll mention it as well. If we're doing steam methane reforming, so in steam methane reforming, what we're basically doing is taking methane and reacting it with oxygen to make CO2 and hydrogen. We're going to capture the CO2 so we can do it. This is why we're going to need to do the CO2 purity measurement. But we're also going to produce a whole bunch of hydrogen. One of the reasons Alberta is, again, uniquely poised right now, because we have very low natural gas prices because we have a lot of natural gas production. We have limited takeaway in terms of pipeline capacity. So we have low natural gas prices. So that makes one of the feedstocks for my steam methane reforming very inexpensive. It means that we can readily make hydrogen at a quite low cost for manufacturing. So, hydrogen is considered one of the feedstocks for a lot of the things that we're seeing in this sort of, if you like, this green revolution that's going on. When we make the hydrogen from methane, though, we will produce CO2, which doesn't sound very green. But if we include carbon capture in there, we refer to this often. This is what people will refer to as blue hydrogen. And so when we're thinking about doing steam methane reforming and making blue hydrogen through carbon capture, it would be nice if we have an analyzer that can measure the CO2 and measure the hydrogen purity as well. And that is, again, one of the unique things about the mass spec is because it has multiple, can measure multiple sample points. We can have one stream doing the CO2 and another one doing hydrogen. So we can do purity applications in both of them. We've actually just recently installed a mass spec here in Alberta as well, doing helium purity. So some clients built a 5/9 purity helium plant, and we're using it to do all the helium purity analysis as well. So this mass spectrometry is a very applicable technology to a lot of things that we're seeing in some of the new chemical processing schemes that are going on. And that are commonplace that this whole process steam methane reforming gets used in is in ammonia production. And so again, ammonia is one of those fuels that we can potentially use in applications, which is going to have zero CO2 emissions when it's burned. That kind of wraps me up on the technical piece of this thing today. Not usually finished early, so it's kind of a new one for me. Give you an idea again about Insight. We carry a number of different product lines. So we'll do everything from water and hydrocarbon dew points and natural gas to, of course, the XTRL mass spec we just talked about, total sulfur analyzers, some of our own manufactured products. And so again, if you've got an analytical application, we are 100% focused on analytical. It's all that we do. And so if you've got an analytical application, we'd love to discuss it with you. From a systems integration side, I just like to run through a little animated slideshow of some of the applications we've done, things from composite samplers out on pipelines, to full analyzer sample systems, automated grab sampling stations. Again, multiple analyzers in a given analyzer shelter and building. We did the whole building for this one. Sample stream switching systems. Again, another analyzer building with automated sampling in it, automated grab samplers, composite sampler again. And so if you've got an application, we'd love to discuss it with you, work with you on what technologies we can possibly put in there to solve some of your problems. It's one of my favorite slides to talk about because we've got the PLC, we've got automated grab sampling stations, got an infrared analyzer here, automated solvent flush to clean the system out, 2 composite samplers, all inside of a large analyzer building. Like I say, you'll get a copy of the slides. And if you'd like to get any more information, you can feel free to contact us. Put a couple people from the sales side of things on here. Tuan and Robert are both available on there. You can visit our website at insideanalytical.com. I encourage you to follow us also on LinkedIn. We tend to post a lot of stuff up there, pictures of systems we're currently building. And with that, if there are any questions or anything else that you'd like to discuss, happy to take them now.